I'm going to leave everything in terms of k, and I'm not going to worry about the value of k until the very end. I have two things I need to do here. The first is I'm going to eventually want to take this as negative k times the limit as t approaches infinity of the definite integral from 0 to t of t times e to the kt dt. But then the question is, how would I evaluate this? I can't use t here. I'd ordinarily use t. I'm going to use p because I can't use p for both things. That makes sense. So I'm going to make a little side trip here and figure out, okay, what is the antiderivative of t times e to the kt dt? I have to use integration by parts. So integration by parts says if you can write this as a times db, the product of two things, then it's going to be that antiderivative is equal to a times b minus the integral of the derivative of a times b. And that's just integration by parts formula. It comes from reversing product rule. A is equal to t, and db is equal to e to the kt. So b would be the antiderivative of e to the kt, going to be 1 over k times e to the kt. If you think about taking the derivative of e to the kt, it would be, so then I just plug these pieces into my pattern. I have a times b minus the integral of dab, so 1 times 1 over k e to the kt dt, and a times b is just t times 1 over k e to the kt. And this one, it turns out I can do. I can pull this 1 over k out front, and I do the same thing I just did. I'm laughing because it ends up looking a little bit ridiculous, but I'm going to rewrite this as 1 over k t times e to the kt minus 1 over k times the integral of e to the kt dt, which becomes 1 over k times t times e to the kt. And then this is 1 over, this antiderivative is again 1 over k times e to the kt by the same reasoning that we used here. So I get 1 over k squared. Right. So I did all of that to get something that I can plug in here. So when I take this expression, which is the antiderivative of t times e to the kt dt, and I take that antiderivative, and now I'm going to do the definite integral from 0 to p of that. What I'm going to be doing is taking this 1 minus k times t to the kt minus 1 over k squared e to the kt evaluated from t equals 0 to p and subtract. So I have 1 over k times t times e to the k times p minus 1 over k squared times e times k p minus 1 over k times 0 times e to the k times 0 minus 1 over k squared times e to the k times. This is equal to 0. This is not, so we have to keep it. But then when we take this expression and we plug in, taking the limit as p approaches infinity, because that is exactly what we needed to figure out here. The limit as p approaches infinity of this whole huge algebraic thing. So here's where we could plug in. At least it's important that k is negative something, because this then becomes e to the, like you can change this negative k because it's negative. Basically what happens is this goes to infinity. Because of the specific value of a that we're working with, which is negative, we're going to end up with this and this. Both of these limits become 0 because you're looking at like e to the negative 0.00121 times e, and as you take the limit as p goes to infinity, that exponential becomes 0, and here it wins the race against p. That and that and that all go away. And so what we're left with here is we're going to carry forward our negative k times the only thing that survived, which is this last term. So the final answer would be negative k times positive 1 over k squared times e to the negative, or just times e to the k times 0, which is going to be negative k times 1 over k squared times 1, which I cancel this negative k with this 1 over k squared, and I just get negative 1 over k. So I would plug in the numbers for k, so my final answer would be negative 1 over negative 0.000121, which would be 1 over 0.000121.